My name is Mark Cruz. I'm a computer researching scientist. I recently just passed the Cisco Certified Network Associate exam. I couldn't think of a better way to celebrate passing the CCNA exam than to do some configurations on the Cisco Modeling Lab platform. So what we're going to do is we're going to start a virtual machine that will act as our Cisco Modeling Lab server. We'll connect to this virtual machine server with the IP address 192.168.1.92. When I configured the virtual machine server, I configured it to get its IP address with Dhcp, so it pulled its IP address from my local area network router, so that way I could use my computer to access this web interface through a web browser. So what I've done here is I've put in 192.168.1.92 into a web browser, and now we're taken to the Cisco Modeling Lab platform. This is the topology we're going to build in the video. First, we'll start with these bottom two local area networks. Then we'll move on to this left side of the network where we'll do some Dhcp configuration stuff, and then finish off the video with some Hotspot routing protocol right before it exits to a layer 3 switch that represents the internet service provider. So the idea is that's your exit gateway. That blue router there is your gateway to the internet. I was using a Surface Book 2 when I used the Cisco Modeling Lab platform. It's got 16 gigabytes of RAM and an Intel Core i7. These topologies are saved as YAML files, known as YAML files. So when you build your topologies, they're stored, in this case, on our virtual machine. But if that were to fail for whatever reason, we would lose our topologies. So the platform has a feature where we can download the lab in a YAML file, which is the .yaml file type. This allows us to back up our topologies and share them with other people. After we click on the Download Lab button and we navigate to our Downloads folder, we can see that the topology was saved in the .yaml file format. So we're going to delete this YAML file, and then we're actually going to go into the Cisco Modeling Lab platform and delete the topology. So now we've completely lost the topology. But what I've done is I've uploaded the YAML file to my GitHub account. In the repository, there's also text files with all of the configuration commands throughout the video. This way you can download the YAML file, import the YAML file into the Cisco Modeling platform, and then copy and paste the configurations from the text file into the Cisco Modeling Lab platform. Or you can also follow along with the video and just have the commands there as a reference in the text file. So we downloaded it as a zip file from the repository, and then we'll drag the YAML file out onto the desktop. I'll open a few of the text files to show the different commands that are used in the configurations. What you will do is copy and paste from the text file into the console of the virtual machines in the Cisco Modeling Lab platform. Now we've come back to the Cisco Modeling Lab platform, and there's that import button in the upper right hand corner of the web browser. So when we click on this import button, it'll take us to a page where it will ask us which files do we want to import. Since we dragged our YAML file to the desktop, we'll look on the desktop, find the YAML file, double click on it, and then click on the import button. And now the topology has been loaded back into the Cisco Modeling Lab platform. And there it is. So what I did is I used GitHub to both back up and share these network topologies and configurations. The neat thing about this platform is you can save topologies. So for example, here I've got a topology that I used when I was studying for the exam to help me better understand Ospf designated router elections. So then I could just have that topology built in there and turn it on whenever I need it. But in this video, we're going to be building that whole big topology from scratch. This is how the interface works. There's a tray of different networking virtual machines that we can load into our topology area. And we're going to build everything with these three devices, a router, a switch, and a desktop. So this is going to be the start of our large topology. It's going to be this first local area network. And what I like to do is I drag out all of the virtual machine devices that we're going to be using, and then make the connections, label everything before I even turn on any of the devices. I found that if you use really good labeling on the setup, it makes the labs a lot more fun and less cumbersome. In this particular local area network, we're going to have 8 desktops, 4 switches, 2 of which will utilize layer 3 technologies, and then 1 router. So right now I'm just kind of setting up how I want the topology to look like. You can make this however you want it to be. And we'll pretty much just be mimicking this topology. And the neat thing about the Cisco Modeling Lab platform is you have these different tabs that you can utilize on the virtual machines. One of them is connectivity and allows me to see which port is connected to which port. And with everything properly labeled, you can see how much easier it is to determine the devices that you'll be working on. So the first thing I do is I go in here and I start labeling the devices. The top router will be central. This first switch will be dist 1. The second switch will be dist 2. And then the bottom 2 switches will be access switches. So this lower left one will be access 1. And the one on the right will be access 2. So for this topology, each of these desktops will be placed in their own VLAN. So I went ahead and labeled each desktop with the respective VLAN that it will be placed in when we start doing our configurations. So after we finish all of our labeling, we're going to start making our connections between the devices. So now that we've finished our labeling, we're going to get into making the connections between the different virtual machines. This particular GUI interface that the Cisco Modeling Lab uses works really well when making these connections between the virtual machines. When you see after proper labeling, it actually labels the column header with the name of the virtual machine, and then a drop-down list of the port that you want to select. You're also allowed to add interfaces to the virtual machines. When the configurations have not been done yet, you can go into the virtual machine and add interfaces to the device. This first part of the topology is going to be a layer 2 ether channel. So what I'm doing here is I'm making 4 Ethernet connections between these two switches so that I can create the ether channel between them. So this is just, I haven't turned on any of the devices. We're just making, it's the equivalent of plugging the cable into the device. So we'll also have a point-to-point connection between this layer 3 switch and the router. We'll have to turn the ports into routed ports, but we'll get into that later into the configuration process. For now, we'll focus on just making the connections here. Between disk 1 and disk 2, we're going to have a layer 3 ether channel. So again, we're going to have 4 Ethernet connections between disk 1 and disk 2. So what we're doing with this other half of the topology on the right here is we're going to do a traditional router on a stick configuration, which means there's only one link between the layer 3 switch and the layer 2 switch that acts as a trunk link to then allow the different VLANs to have tag traffic flow across the trunk link, so then that the layer 3 switch can do routing between the VLANs, and that's kind of what routing on a stick is referred to as. So the last piece for us here is we're just going to tie in our connections from our access switch to our PCs. And then this is our first local area network topology that we'll be working with. And now that we've made our connections, labeled everything properly, we can start turning on the devices. Later in the video, we'll see that depending on which license you purchased, you can only have so many nodes operating in your topology at one time. So the desktops provided with the Cisco modeling labs are configured to pull IP addresses with by DHCP. You can also configure them statically by editing the startup configuration. Essentially, what these desktops are, they are Alpine Linux boxes. So they actually use a Linux operating system. So here I just have 2 Linux commands to set the default gateway for the desktop, and then the IP address of the desktop statically. The default gateway command is that route add default GW, the gateway IP address, ETHO for Ethernet 0, and then the static IP address command is IPADDR add the IP address with the subnet mask dev and then ETH0. And then all you have to do is change the default gateway and the IP address for each machine, and then you can just copy and paste the configuration to each virtual machine. The other thing to be careful when you do this, you have to click that save button there right on the upper left of the notepad. If you don't click save, then it will revert to the default and will not save the startup configuration. So you have to click save whenever you edit these startup configurations. So now I'm going to go into each desktop and statically assign the IP and the default gateway. So now we're ready to turn on our devices. So we start by turning on DIS1, DIS2, Access 1, and Access 2. With smaller topologies like this, the performance is excellent. The devices, their startup configurations load very quickly. As the topology grows and we add more virtual machine devices to the topology, the performance of the Cisco Modeling Lab platform starts to suffer a little bit. The loading times, for example, when you start new devices is much longer when you have 20 nodes as compared to just these 4. Now that the virtual machine has started, we enter enable mode using the enable command, and then the global configuration mode by using the configure terminal command. Then we use the host name access1 command to give the device its host name. And then we also enter line configuration mode with the command line console 0 to enter the logging synchronous command. That way, when we get syslog message updates during our configurations, it won't affect the commands that we type in the command line. It'll keep everything looking much more neat as well. The first thing we will do is configure the ether channel between DIS1 and Access1. So the first thing we do is enter the interface range gigabit Ethernet command. This way we can enter all 4 Ethernet ports configuration mode at the same time. The configuration for the ether channel is identical between the 4 ports. This way we can just enter the command one time for all 4 ports. So the first command we enter is the switch port trunk encapsulation.1q command. This configures the interface's encapsulation protocol that they should use on the frames that are traveling over the trunk links. We also enter the switch port mode trunk command to statically assign the operational mode of the port as trunk mode. And finally, we enter the channel group 10 mode passive command. This sets the channel group protocol to the link aggregation control protocol, and more specifically, they're set to passive, which means they will become link aggregation control protocol links if the other side of the link is actively trying to become a link aggregation control protocol port. So next we'll move into DIS1 and do the layer 2 ether channel configuration. Before we do that, we'll give it a host name of DIS1 and then enter line configuration mode to enter the logging synchronous command to keep our syslog messages looking clean. Next, we enter the interface range gigabit Ethernet command. again, to enter all 4 ports simultaneously to enter identical commands. This is where the Cisco Modeling Labs platform works really well when making these types of configurations. This way I can reference the topology interface just to double check before I make any configurations. So now that we're in interface configuration mode for these 4 ports, we enter the switch port trunk encapsulation .1q command, followed by switch port mode trunk to statically configure all 4 ports as trunk links. Finally, the channel group 10 mode active command to make these 4 ports actively try to become link aggregation control protocol ports. They'll communicate with the ports on the other side of the ether channel, which will bring up the ether channel. And we can confirm this by using the show ether channel summary command. And from the output of the command, we can see that the S means layer 2, U means in use. So this ether channel is a layer 2, it's in use using the LACP protocol. Now we'll enter the interface configuration mode for each of our desktop ports. We'll configure them to be static ports by entering the switch port mode access command. And then we'll also assign the port to participate in a specific VLAN by entering the switch port access VLAN command. So when we do this, all of the 4 ports that are connected to the desktops will be in separate VLANs. And then we'll use inter-VLAN routing to communicate between the desktops. When doing these types of configurations, it's really useful to use the up arrow. Here you can see I just up arrowed to the last switch port access VLAN 30 command, deleted the 30, put in a 40, and now I have the correct configuration. It can save you time when you're doing your configurations to use the up arrow. These are layer 3 switches, so we use the IP routing command in global configuration to enable the routing features on the layer 3 switch. This layer 3 switch will be participating in inter-VLAN routing, so we need to create the 4 VLANs that'll be participating in the inter-VLAN routing. So we use the VLAN 10, 20, 30, 40 to create the 4 VLANs we need simultaneously. Next, we use the interface VLAN 10 command to enter interface configuration mode for VLAN 10, and we configure the IP address 192.168.1.1 for a /24 gateway IP address for VLAN 10. We statically assigned the default gateway IP addresses on all of our desktops. And then we gave our desktops static IP addresses. So when we turn on our desktops, we'll be able to ping our default gateways. The other part of this configuration requires the no shutdown command. When you enter the interface configuration mode for a VLAN, the VLAN is shut down by default. So here I'm entering the no shutdown command to bring the interface up. And we can see here we're getting the syslog messages that interface VLAN 30 has changed its state to up. Now enter the show IP interface brief command to confirm that the VLAN's IP addresses are correct. And then that's the last part of the inter-VLAN routing configuration over the layer 2 ether channel. Then we can test the configuration by using the ping command to ping our default gateways. and then our neighboring desktop computers, which are in different VLANs and different subnets. And you can see here I pinged my default gateway, and now I'll ping the IP address of the desktop in VLAN 40. And then we can see we're getting a response. So we've successfully set up inter-VLAN routing on this left side of the local area network here. Next, we're going to move into layer 3 ether channel configurations on dist 1 and dist 2. So this particular switch has 9 different links. So it can get a little confusing when you start to try to configure dual ether channels. But since we did our proper labeling, we can see here on the left is dist 1, on the right is dist 2. And with that connectivity tab, we can verify which ports that we need to configure. So now we'll enter the interface range gigabit Ethernet 1/0-3 command to enter the interface configuration mode of those 4 ports. For the layer 3 ether channel, we have to enter the no switch port command to turn the ports into routed ports, giving them layer 3 capabilities, which means we can assign the interfaces an IP address. So what we'll do is bundle these 4 ports into an ether channel using the channel-group 15 mode on command. So now that the 4 ports are participating in this ether channel and that we entered the no switch port command, we can assign an IP address to the port channel itself. And so we'll enter the IP address 10.99.1.255.255.255.252 command to give that port channel interface an IP address. Then we'll do the exact same configuration on dist 2 to complete the layer 3 ether channel configuration. So here on dist 2, we'll use the interface range gigabit Ethernet command to enter the 4 ports on the other end of the layer 3 ether channel. We'll enter the no switch port to turn the ports into routed ports, giving them layer 3 functionality. And then we'll also enter the channel-group 15 mode on command to have these 4 ports participate in the same ether channel. And then finally, we'll enter the port channel interface and give it an IP address in the same subnet as the IP address on the ether channel on dist 1. So we'll enter the IP address 10.99.99.2.255.255.255.252 command to give it an IP address in the same subnet. And that'll complete the layer 3 ether channel configuration. To verify the configuration, we use the show ether channel summary command. So the R refers to a layer 3 configuration, and the U refers to in use. So this port channel 15 is a layer 3 port channel, and it's in use. So now we'll come back to dist 2, enter a show ether channel summary command, and we can see the SU refers to layer 2 in use, and the RU refers to layer 3 in use. So this switch has a layer 2 and a layer 3 ether channel configured on it. So now we're going to move back into access switch 2 and configure the desktop ports to be access ports. The first one we'll do is interface gigabit Ethernet 0/1. Once we're in interface configuration mode, we enter the switch port mode access command to configure it to be a static access port. And then we'll enter the switch port access VLAN 50 command to have this port only participate in VLAN 50. And then we'll repeat the configuration on each port that is connected to the desktop with the respective VLAN that it will participate in. So again, for example, here at the end, we use the switch port access VLAN 80 command for gigabit Ethernet port 1/0. And for the last part of the configuration, we'll go into interface gigabit Ethernet 0/0 and configure it to be a trunk port with the switch port trunk encapsulation .1q command, followed by the switch port mode trunk command. Now we'll complete the configuration for access switch 2. Now enter the do show interfaces gigabit Ethernet 0/0 switch port command to verify the operational mode is set to trunk. With most show commands in global configuration mode, if you use the keyword do, you can execute the show command in configuration mode, which is useful. As we can see here, we can look at the configuration of the switch port without leaving configuration mode. For the last part of the configuration, we'll move back into DIS2, which is a layer 3 switch that has its routing capabilities enabled. And so now we'll move into interface gigabit Ethernet 0/0 and enter the no switch port command to turn it into a routed port, which gives us the ability to assign the port IP addresses. It also gives us the capability to assign IP addresses to sub-interfaces. So in this particular example, we'll interface gigabit Ethernet 0/0.50 to enter the sub-interface configuration mode for this port. Once we're in sub-interface configuration mode, we have to enter the encapsulation .1q VLAN command to configure the encapsulation type for the sub-interface and what VLAN it will participate in. And then we can assign the sub-interface the IP address. So for this first VLAN, the IP address will be 192.168.5.1, 255.255.255.0. Now we'll go into each sub-interface, configure the encapsulation type and the VLAN that it will participate in, and its IP address. And then that will finish the router on a stick configuration and allow these desktop PCs the ability to ping each other, indicating that they have network connectivity. Now that I've finished the configuration, I use the show IP interface brief command just to double check the IP addresses are correct, and then we're going to turn on all the desktops and then start pinging one another to verify our network connectivity. So on this first desktop, we'll ping ourselves just to make sure everything's okay. And then now we'll ping our default gateway, see we're getting a response. And then we'll ping the PC on the far side of the local area network. So this proves that we've configured router on a stick for this layer 3 switch. So what we have now is a local area network on the left that's using inter-VLAN routing to communicate with 4 subnets on 4 different VLANs, and then the layer 3 switch on the right, Dis2, is using router on a stick to have 4 subnets and 4 different VLANs for these 4 different desktops. So now they cannot ping each other without a static route from the local area network on the left to the right, and then a static route on the local area network from the right to the left. So the first static route we'll configure is on Dis2. So we enter the IP route 192.168.1.0, 255.255.255.0, 10.99.99.1 command. The 192.168.1.0 is the other local area subnet, and the 10.99.99.1 address is the port channel address on dist1. So that's our next hop IP address in the static IP routing configuration. Each static route will have the same next hop IP address, and then we'll go in and enter the IP address and subnet mask for each local area network on the other side to configure our 4 static routes to the other local area network. If we did a ping command right now, it would still fail because dist1 doesn't have a route back to any of the other subnets on the right side of the network. So now we have to go to dist1 and configure static routes from the left side of the topology to the right side. To remove a static route from the configuration, you enter the keyword no in front of the IP route command. So for example, I'll come in here and type in the wrong static route of the 192.168.4.0 subnet. That subnet is on this left side topology. So it's the incorrect static route configuration. So we'll go ahead and enter the command and then use the no command to then remove the static route configuration. There are a lot of Cisco configuration commands that allow you to put the keyword no in front of them to return the configuration to before you enter the command. So now we'll use the up arrow, enter the correct IP address of 192.168.5.0. And then we can use the up arrow, change the subnet numbers, and now we have our 4 static routes to dist2. Then we do the do show IP route to verify our static route configuration. And there we can see our static routes. Now we can go back into the VLAN 10 PC and attempt to ping the VLAN 80 PC. And we can see that we're getting a response, which lets us know our static routing configuration is correct. So now we're going to keep expanding our topology. We'll begin by placing 4 switches in the center, or what will be the center of the topology when we're finished. These 4 switches are going to have a full mesh topology when we're done. And then we're also going to add a router here that will eventually connect to another router where we'll configure some more networks. So the first thing we're going to do is label the central switches as core 1, core 2, core 3, and core 4. This router we're going to call area 51, and it's going to be connected to another router that will connect to the president and the vice president's personal computers. And then this Area 51 router will also have two local area networks off it representing the Speaker of the House and higher level generals. So after labeling it at Area 51, we add this router up here on the upper left for our branch 1 network that we're going to build. And then this upper right router we label Secure Zone, which is going to demonstrate some security features that Cisco offers. So now that we have everything labeled, we'll start making our connections. Every router's gigabit Ethernet 0/0 port will connect to the switches. So that'll be our first connection that we'll make, is from the switches to the routers. And then now we're going to make our full mesh topology connections and then start turning on the virtual machines and start our next part of the configuration process. So we'll turn on all the devices that we'll need for this next part of the video. So we're going to focus on the Area 51 part of the network. We're going to insert another router and call it Area 51 Vault. These routers will be connected to each other, and then each router will be connected to a switch and each switch will have two local area networks off of it. So after I drag out all of the devices, we'll start labeling them. So we just label this first switch VIP switch 1 for VIP, and then we'll label the other switch VIP switch 2. And now that everything's labeled, we can start making our connections. These 4 desktops are going to use static IP addresses. Each desktop will be in its own VLAN, so we'll have 4 different VLANs. I just go over here to the VLAN 80 PC and copy its static IP address configuration, and then just paste it over here on the Speaker of the House's desktop to have it, and then just change the IP address to what I want it to be. So for this network, it's going to be a 192.168.10.0 network. So my IP address will be 192.168.10.100, and the default gateway is 192.168.10.1. Before adding the static IP addresses to the other desktops, I'm going to label everything. So this first one will be Speaker for Speaker of the House, General for higher level generals, and then POTUS for President of the United States, and then Vice POTUS for Vice President of the United States. So we'll finish out our static IP addressing pre-configuration on the rest of the desktops, and then we'll power them on, and they will be ready to go. So now we're going to go into VIP switch 1, and we're going to configure the trunk link between VIP switch 1 and Area 51 and the access links to the desktops. So we'll give it a host name and then enter the logging synchronous command in line configuration mode to keep our syslog messages looking clean. Now we'll enter the interface configuration mode for Gigabit Ethernet 0/0, which is the port connecting to Area 51. And we'll enter the switch port trunk encapsulation .1q command, followed by the switch port mode trunk command to have the port be statically configured to be a trunk port. We'll start with Gigabit Ethernet 0/1, which is the speaker of the house's port. We'll enter the switch port mode access command, followed by the switch port mode access VLAN 10 command. Then we'll use the up arrow to get into the interface configuration mode for Gigabit Ethernet 0/2. We'll enter the switch port mode access command, followed by the switch port access VLAN 20 command. And that will complete the VIP switch 1 configuration. And now we'll move over to VIP switch 2 and configure it. Like all the other devices in the video so far, we'll start by giving the device a host name and then entering the logging asynchronous command to help keep our syslog messages looking clean. Now we'll enter the interface configuration mode for Gigabit Ethernet 0/0, which is the port connecting to the Area 51 vault router. We'll enter the switch port trunk encapsulation .1q command, followed by the switch port mode trunk command to make this port a static trunk port. Next, we'll configure the access ports. The first one will be the President's port, which is Gigabit Ethernet 0/1. We'll use the switch port mode access command to configure it to be a static access port, followed by the switch port access VLAN 77 command. Now we'll go into interface Gigabit Ethernet 0/2, enter the switch port mode access command, followed by the switch port access VLAN 7 command. And that will finish off the configurations for the VIP switches. All of our devices are now powered on, and the first thing we will do is go into the Area 51 router, configure its host name, and the logging asynchronous command in line configuration mode. Then we'll enter the command interface Gigabit Ethernet 0/2 to enter the configuration mode for the port connecting to VIP switch 1. We're going to enter the no shutdown command because routers have their ports turned off by default. So you have to enter the no shutdown command to enable them. Once the port is enabled, we'll jump into the sub-interfaces and configure them. The first sub-interface we'll configure is Gigabit Ethernet 0/2.10. Once we're in sub-interface configuration mode, we use the encapsulation .1q10 command, followed by the IP address 192.168.10.1, 255.255.255.0 command to configure the sub-interface to be the default gateway for VLAN 10, which is the speaker's VLAN. Now we'll use the up arrows to go back to the sub-interface configuration command and modify it to port Gigabit Ethernet 0/2.20. Use the encapsulation .1q20 command, followed by the IP address 192.168.20.1, 255.255.255.0 command to finish the router on a stick configuration for this left side of the network. We're also going to configure an IP address on the connection between Area 51 and the Area 51 vault, which is Gigabit Ethernet 0/1. We're going to give it the IP address 10.97.97.1, 255.255.255.240. This will give us 14 usable IP addresses in the subnet, and that becomes more important later when we do the NAT configuration, the network address translation. But for now, it's like any other interface. We gave it the IP address in a subnet, enter the no shutdown command to enable the interface. So now we've finished our configurations on this left side network here. So we'll power on all of our devices, and then we're going to move into the Area 51 vault router, assign it its host name, and like with all the other devices, enter line configuration mode to enter the logging asynchronous command to keep our syslog messages looking clean. The first thing we'll do is we'll go into interface Gigabit Ethernet 0/1 and enable the port with the no shutdown command. After the port is enabled, we'll go into the sub-interface configuration mode for Gigabit Ethernet 0/1.77. Once we're in the interface configuration mode, we'll enter the encapsulation .1q77 command, followed by the IP address 192.168.77.1, 255.255.255.240 command. This gives us 14 usable IP addresses for the subnet. So it's a little bit more secure because there's only 14 IP addresses that can be on the local area network. Whereas if you use a /24, there's 254 possible IP addresses. If an attacker needs an IP address for whatever reason, they will only have 14 possibilities as opposed to 254 with the /24 networks. So now we use the up arrow and then enter the encapsulation .1q7 command, followed by the IP address 192.168.7.1, 255.255.255.240 command. And And so now we've configured both of our sub-interfaces as default gateways for our two different VLANs, which are 7 and 77. Now we will configure an IP address on the interface that is connected to Area 51, which is Gigabit Ethernet 0/0, and we'll give it the IP address 10.97.97.2, 255.255.255.240. And so now the interfaces between these two routers are in the same subnet. I use the show interface brief command to double check the IP address assignments are correct. When I copy and pasted the static configuration into the president and the vice president's static IP address, I used a /24 IP address in the startup configuration. So if you want to edit the configurations, you have to wipe the node. And then once you wipe the node, it'll give us the ability to edit the startup configuration. So we'll go in, change the correct subnet mask to a /28, which is the .240 subnet, and change the static IP address to 192.168.77.7, because we only have 14 IP addresses in that first range. So using a 7 is okay because it's in that range of usable IP addresses. Now we have to do the same thing on the vice POTUS. We'll have to wipe the configuration, update the subnet mask and the correct IP address, and then save the configuration, boot up the desktops, and now they are ready to go. For the initial configuration, we're going to want these 4 PCs to have IP connectivity between them. We'll achieve the IP connectivity with static routing on this network. So the first command we'll enter on Area 51 Vault is the IP route 192.168.10.0, 255.255.255.0, 10.97.97.1 command. This will configure the first static route, and then we'll use the up arrow and modify the IP subnet and enter the command to configure the second static route. For this next part of the video, I wanted to demonstrate the no command really quick. So here we'll put in a static route to a /24 network where the static configurations are for /28 addresses. So without the correct static IP route, we won't have IP connectivity, network connectivity. Using the show IP interface brief command can be tricky because there's no subnet mask. Well, what we're about to do is use the no shutdown command on the link between Area 51 and Area 51 Vault. So we'll enter the no shutdown command to enable the port. And that still won't fix our problem because our static route is configured for a /24. And we need it to be configured as a /28. The Area 51 Vault router is configured correctly. We use the show IP route command to verify the static routes are okay with the proper subnets. Now we'll come back to Area 51, do a show IP route command. And we'll see the 2 incorrect static routes that are configured on the router. So what we can do is use the up arrow to go back to the routes we want to get rid of, and then use the word no in front of them to remove them from the static routing configuration. So use a do show IP route to just verify that I removed the static route from the configuration. So we still have to remove the 192.168.77.0/24 static route. So we'll just use the up arrow again and then put the no keyword in front of the static routing command to remove the static route. And then now we'll configure our last static route, which is to the vice POTUS PC. And so now when we do the do show IP route, we can see that we have the correct subnet masks on our static routes. And now we'll have IP connectivity between all 4 subnets. Now we'll ping the president's PC from the speaker's PC to verify IP connectivity from the left side network to the right side network. Then we'll also ping the vice president's PC. The next part of the video will cover a dynamic routing protocol called Open Shortest Path First, known as Ospf. Since we use IPv4 in the video, we'll use Ospf version 2. If you were using IPv6, you'd use Ospf version 3. We enter router configuration mode using the router Ospf 50 command. The 50 refers to the process ID, which is local to the router only. So other routers don't have to use the same process ID. They will need to be in the same area for this particular example. We'll just be using one area, and all of the routers will have to participate in area 0. So the first thing we do in router configuration mode is enter the router-id command. We'll give the router an ID of 8.8.8.8. This will be used later to determine the designated router and the backup designated router. If you don't configure the router ID, the router will choose the highest active loopback IP address and use that as its router ID. And if it doesn't have that, it will use the highest active interface's IP address on the router as the ID. So by using the router-id command, we can control the designated router election process. The reason for this default configuration is convenience. You don't have to configure the router ID. It will configure it itself and then participate in Ospf. It's also a disadvantage if you do it that way, because then you don't have control over the ID itself or the designated router election process for Ospf. In router configuration mode, we could use the network command to advertise all of the networks that we have on router 1. Most of the video, we will be using the interface configuration for Ospf. So to enable the advertisement of the routes, we will actually enter the interface configuration mode of the Ethernet ports and enter the IP Ospf 50 area 0 command. And this is the command that advertises the IP address on the interface. So now that we have the router ID configured, we're going to configure the IP address on the gigabit Ethernet 0/0 interface. So we go into interface configuration mode and enter the command IP address 10.10.10.4 255.255.255.224, and this will give us 30 usable IP addresses in the subnet. And then we enter the no shutdown command. The other command we need in interface configuration mode is the IP Ospf 50 area 0 command. This command is what configures the routing protocol to advertise the subnet. we move back to the left side of the topology to enter back into dist1. We're going to configure dist1 to participate in Ospf. First, we'll go into global configuration mode to enter the router Ospf 50 command. Next, we'll enter the router ID 0.1.1.1 command to give it the router ID. Then we enter the interface configuration mode for Gigabit Ethernet 3/1, which is the port that connects to the central router. We enter the no switch port command to turn the port into a routed port, so we can assign it an IP address of 10.98.98.255.255.255.252. Then we enter the no shutdown command and the IP Ospf 50 area 0 command to have this interface now participate in Ospf. Now we move back to the central router, and when it boots up, we'll start the configuration. So like with all the other devices, we'll begin by giving the router a host name and then entering line configuration mode to enter the logging synchronous command to keep our syslog messages looking clean. We enter the interface configuration mode for Gigabit Ethernet 0/0 to assign it the IP address 10.10.10.3, 255.255.255.224, followed by the no shutdown command to enable the interface. Now we enter the Gigabit Ethernet 0/1's interface configuration mode and assign it the IP address 10.98.98.1, 255.255.255.252. We enter the no shutdown command to enable the interface. And then we use the IP Ospf 50 area 0 command to have this interface also participate in Ospf. We go back into interface Gigabit Ethernet 0/0 to enter the IP Ospf 50 area 0 command to have this interface participate in Ospf. And then we'll actually go back into router Ospf mode by using the router Ospf 50 command. And then we're going to configure a router ID of 7.7.7.7. And now we can see our neighbor adjacency has gone from loading to full. And so now the central router and Area 51 are now neighbors. Area 51 has the 8.8.8, and then dist1 has the 0.1.1.1. So the central router right now has two different routers that it's participating in Ospf with. Now we can do some network connectivity testing by using the ping command on dist1 to try to ping the Gigabit Ethernet 0/0 port of Area 51. And then we can see the ping is successful, which means we have IP connectivity. When I use the show IP route command, we can see here that I have a route to the 10.10.10.0/27 network. So when I go to ping something in that IP network, dist1 knows about it, forwards it to the central router, and then forwards it to Area 51. For this next part of the video, we return to the Area 51 network, and we're going to do some network address translation configurations. First, we're going to do a static IP NAT configuration on Area 51. For this particular example, we have two static NAT translations we need to configure. So we use the IP NAT inside source static command. With this command, the first part of the command is the inside IP address. So in this case, it will be the speaker of the house's PC to what the outside post NAT translation IP address will be. In this case, it's 10.10.10.11. And now we have to configure a second static NAT translation for our other desktop, which is the higher ranking general's PC. So we use the up arrow to get the IP NAT inside source static command back. Then we modify the inside IP address to be the general's PC as the inside address, and then 10.10.10.12 for the outside IP address. Then we need to enter the interface configuration mode for port gigabit Ethernet 0/0. This is the port that connects to the routers, and we need to enter the IP NAT outside command. Then we need to enter the port facing the desktops, which is gigabit Ethernet 0/2, to enter the IP NAT inside command. And that will finish our static NAT configuration. So I use a show IP NAT translation command to show that the inside global addresses match up with the inside local addresses. Inside local is the port facing our desktops, and inside global is the post NAT translation IP address. And now I'll ping the IP inside global address for the general's PC, which is 10.10.10.12, to verify that we've got IP connectivity. Now we'll move back to this left side of the topology, back into dist1, which is one subnet over, and then we're going to ping the inside global address, which is the outside IP address, part of the NAT configuration. And once we ping it, we can see that we have IP connectivity. I decided to change the host name of the Area 51 vault router to Vault 51. So now what we're going to do on the Vault 51 router is we're going to configure dynamic NAT translation with the port address translation. So the first thing we have to do is define a range of IP addresses that we can use in our NAT pool. In this case, we're going to use 14 NAT IP addresses in our pool. So we use the IP NAT pool command, followed by the name of the pool. In this case, it's the executive branch. Then we have to enter the low range of the IP addresses, followed by the highest IP address in the range. So in this case, it'll be .16 and .30. we use the net mask 255.255.255.240 to finish off the command and define our network addressation pool. The next part of the configuration requires us to use an access control list to define the network that will be translated. So in this case, it will be the 192.168.77.0 network, which is the President's network, and then the 192.168.7.0 network, which is the Vice President's network. And we have to use a wildcard mask of 0.0.0.15 to configure our subnet. And then I use a do show IP access list command to verify the access list. And here we can see we've got our two permit statements with their wildcard bits displayed in the show output. And this confirms that we've configured our ACLs properly. So now that we have an ACL and an access list pool, we're ready to configure dynamic NAT translation with port address translation. So the command we'll use is ipnat inside source list 7, which is referencing our access list, followed by pool, and then executive branch, referencing the name of our NAT pool, followed by the overload command, which is what configures port address translation. Port address translation allows multiple hosts to use the same inside global IP address. So what that means, for example, if all the inside addresses were 192.168.1.2.3 and .4, they would all be represented on the outside by an IP address of 10.10.10.10, for example, followed by whatever port is used in the connection for the socket. And then those different port numbers allow the same IP address to be used for the NAT configuration. And then you can have 65,000 different ports. So theoretically, you could use the same IP address for those 6,500 connections. And then we also have a range of 16 of those to use, so 16 times 6,500 possible connections that we could have. And that's what makes port address translation valuable and why it was implemented to help use IPv4 addressing longer. A big problem of IPv4, of course, is running out of IP addresses. Network address translation and private network addressing were used to extend the life of IPv4. You could also argue that the static NAT configuration is more secure because over there's only the two IP NAT translations, where over here we could have thousands of possible connections, which could make the network less secure. And also an argument to be made that if you knew the static IP inside global IP address, that's less secure. So the argument more becomes just awareness of the potential security risks for each type of configuration. And then there's other things you can do to mitigate those risks. The last part of the configuration requires us to enter gigabit Ethernet 0/0 to enter the IPNAT outside command. The last part of the configuration requires us to enter the IPNAT inside command on our sub interfaces. So we'll go into configuration mode for each sub interface and then enter the IPNAT inside command. So first we'll use the interface gigabit Ethernet 0/1.7 command to enter the IPNAT inside command. And then we just use the up arrow, modify the subinterface to 1.77, enter the IPNAT inside command to finish the configuration for dynamic NAT with PAT. To trigger the IP NAT configuration, I'm going to ping the 192.168.10.100 IP address. So even though the ping was not successful, we go into the router, use a show IP NAT translation command, and we can see the president's IP address of 192.168.77.7 was translated to 10.97.97.17, and it's using port 18. The Cisco Modeling Lab desktops are configured for secure shell connections by default. So what we're going to do now is try to secure shell into this left side network general PC, and it fails, but still we go in and to the router, do a show IP NAT translation, and now we can see the protocol type was a TCP connection, which was the SSH temp, using the same 10.97.97.17 address, but with a different port number, this time 57.850. And that's the translated IP address, and the outside local address was the address we were trying to secure shell into. So now we're going to return to dist1, and we're going to configure our inter-VLAN subnets to participate in the Ospf dynamic routing protocol. So the first thing we do is we go back into dist1, and then in global configuration mode, we enter the command router Ospf50 to enter router configuration mode. This time we'll advertise the networks in router configuration mode instead of interface configuration mode. To do that, we use the network command followed by the subnet that we want to advertise. In this first case, it's 192.168.1.0 with the wildcard mask of 0.0.0.255, followed by area 0 to finish the command. This will then advertise that subnet to all of the other routers participating in the Ospf area. Once we enter the command, we just simply use the up arrow and then modify the subnet to be advertised. So here I go in and change 192.168.2.0.3.0.4.0 with the same wildcard mask and area. Now we'll go back into our other Ospf routers and issue the show IP route Ospf command to show the Ospf learned routes on the router. And here on the central router, we've learned our inter-VLAN routes. So that's pretty neat. We can see these 4 different subnets were learned by Ospf. Their next top IP is 10.98.98.2. So now we'll come back into area 51, and we'll use the show IP route Ospf command. Since this router is participating in the Ospf area, it also gets the routes to our inter-VLAN routes on the left side of the topology there. So next we're going to piece in VLAN 50, 60, 70, and 80 into the Ospf topology. So what we'll do here on dist1 is we'll configure the port channel to participate in the Ospf configuration. So we enter interface configuration mode for port channel 15, enter the IP Ospf50 area 0 command. Then we'll move to dist2, enter the interface configuration mode for port channel 15 on dist2. Then we'll enter the IP Ospf area 50 command. So now this ether channel link is also participating in the Ospf. So now we're going to move into dist2 and configure the Ospf routing protocol version 2 on it. So we'll start by entering router configuration mode with the router Ospf 50 command, and then give it a router ID of 0.0.1.1. After that, we'll move into the sub-interfaces and enter the IP Ospf area 50 command. The first subnet we'll go into is interface gigabit Ethernet 0/0.50, and then we enter the IP Ospf 50 area 0 command. And then we can use the up arrow, change the sub-interface, use the up arrow, enter the IP Ospf 50 area 0 command for all 4 sub-interfaces. And now these sub-interfaces are also participating in the Ospf configuration for area 0. So now we'll go back into the central router and we'll do a show IP route Ospf command. And as you can see, now we've got all 8 subnets in our routing table for the central router. Now we'll jump over to the area 51 router, do a show IP route Ospf command, and we can see that we have all 8 subnets in our routing table for the area 51 router. This is what makes dynamic routing protocols so special. It's because here on area 51, we did a pretty minimal configuration, and now we have a pretty good routing table to the rest of the topology because we have this router participating in Ospf, communicating with the other routers to find routes on the network. This next section of the video is going to cover the upper left-hand corner of the topology. We're going to turn a router into a Dhcp server, have another router use the IP helper -address command. We're going to configure a switch for Dhcp snooping and dynamic Ipr inspection. So just like the other sections of the topology, I dragged out a switch and 4 desktops. Here I add a second router, and we're going to label it expansion 1. Then we'll move into the switch, label it Snoop Switch, and then we'll connect all of the desktops to the switch. We're going to leave the expansion 1 router alone until we configure this first Dhcp network off of the Snoop Switch. The desktops on the Cisco Modeling Lab platform will pull a Dhcp IP address automatically if they're on a subnet with a Dhcp server. As I build a topology, I'm turning on the network devices. That way, it takes some time to build the topologies, so you might as well have your network devices trying to boot up while you're building these topologies. So we're going to go ahead and turn on a few more virtual machines, core 1, core 2, branch 1 in the Snoop Switch. As your topologies grow, the performance and the speed of the virtual machine starts to suffer a little bit. You can see my CPU is pegged out at almost 100% there. And here we get a warning, high system load. So while these new network devices are booting up, we're going to go ahead and build the second Dhcp topology. We won't do any configurations on the second switch, but we will configure the expansion 1 router to use the IP helper address to get to branch 1 for its Dhcp configuration. We're going to turn our attention to the upper right-hand corner of the topology to the secure zone router. We're going to connect a switch to the secure zone router, and then 3 desktops off of the switch. Here we'll be applying some ACL concepts and showing off the Cisco iOS security features. This switch is going to be labeled Secure Switch. We won't do any configurations on it. So now we'll connect the secure switch to the secure zone router. We'll drag out 3 more desktops and connect them to our switch. We're going to label the desktops now. This first one will be SSH. This next one will be Telnet. And the last desktop is going to be IP. What we'll be doing here is blocking those types of traffic to those PCs. So we're going to block SSH traffic to the SSH PC. So now that we have our network devices powered on and our topology built, we're going to start with branch 1. We're going to give it its host name, and then we're also going to enter the logging asynchronous command in line configuration mode to keep our syslog messages looking clean, just like with all the other network devices we've configured so far. Next, we'll enter Gigabit Ethernet 0/0's interface configuration mode to give it the IP address 10.10.10.1, 255.255.255.224. And then we'll also enter the IP Ospf 50 area 0 command to have this router's interface participate in the Ospf dynamic routing protocol. We'll also enter the no shutdown command to enable the interface. And then real quick, we're going to go into the secure zone router. We're going to give it its host name of secure zone. Enter the logging asynchronous command in line configuration mode to keep our syslog messages looking clean. And then we're going to go into the interface Gigabit Ethernet 0/0, go into its interface configuration mode, and configure the IP address 10.10.10.2, 255.255.255.224. And then we'll also enter the no shutdown command and the IP Ospf 50 area 0 command to have this interface participate in the Ospf routing protocol. We also need to set the router IDs. So we're going to use the router ID 2.2.2.2 command in router configuration mode. We'll come back to the branch 1 router, and we're going to enter the router configuration mode with the router Ospf 50 command. And then we're going to give it a router ID of 1.1.1.1. There is a command called clear IP Ospf processes. When you make changes to a configuration, especially with the router IDs, if you change the router ID, you have to clear the IP Ospf processes, and then that will update your adjacencies and therefore updating the router ID. So now we got all of those syslog messages letting us know about our adjacencies. We've actually got 3 neighboring routers off of the same interface with this particular topology. Now that the secure zone router is participating in the Ospf area, it picks up all of the routes that are in the dynamic routing protocol. So we get this entire left side topologies, subnets in our routing table. And so now we'll come to the far side here, VLAN 80, and then we're going to ping the interface of the secure zone router and the branch 1 router. And we can see here we're getting the responses. The more virtual machines we have here on our topology, our performance will suffer. So what I'm doing here is I'm just turning off a lot of these virtual machines during the initial configuration. That way when we're doing our commands, we don't have to wait as much. Once you get everything up and running, you can leave it up and running, but during the initial configuration, it helps to reduce the amount of nodes. So we'll keep a few on just for like testing, but we're going to turn a lot of these nodes off and then move on to the upper left-hand corner of the topology to do the Dhcp configuration. The first device we'll configure on this upper left-hand topology is the Snoop Switch. So first we're going to give it its host name of Snoop Switch, and then we'll enter line configuration mode to enter the logging synchronous command. The first command we'll enter is IP Dhcp Snooping. This enables the feature, and we can verify this with the do show IP Dhcp Snooping command. This way we stay in global configuration mode and we can check to see the feature is turned on. And there from the show output we can see that the feature is enabled. Once the feature is enabled, we have to specify the VLAN to do the Dhcp snooping on. This particular switch, we're only going to be doing Dhcp snooping on VLAN 1. But to demonstrate that you can do it on more than one VLAN, we're going to enter the IP Dhcp snooping 15 and 1530. Now when we do the do show IP Dhcp snooping command, it'll show us the VLANs that are participating in the Dhcp snooping. And there we can see 1, 15, and 1530. Now we'll turn off Dhcp snooping on VLAN 15 and 1530 just by using the up arrow and then putting the keyword no in front of the command. And so now Dhcp snooping is only configured on VLAN 1. For this particular configuration, we're going to disable the insertion of option 82. Typically layer 3 switches, it's okay to have the insertion of option 82 enabled. But if you're going to be using your switch as a layer 2 switch, it should be disabled. So we achieve this with the no IP Dhcp snooping information option command. Now when we do the do show IP Dhcp Snooping command, we can see that we've disabled the insertion of option 82. Option 82 has to do with the DHCP relay information, and it's recommended that for layer 2 switches you disable the switch, so we've gone ahead and disabled this feature. For the next part of the configuration, we're going to enter the error recovery cause DHCP-rate-limit command. And then we're also going to enter the error disable recovery interval 900 command. The 900 refers to seconds. What this means is the port will change its status to error disable if the port exceeds the DHCP rate limit. It will keep that status for 900 seconds, and then it will recover itself by re-enabling itself after the error. Dhcp Snooping by default has the port setting set to untrusted. Anytime you are connecting to the DHCP server or another switch, for example, you'll want to trust those ports. So for this example, we're going to trust the port connecting to branch 1 and expansion 1. So I use the interface range gigabit Ethernet 0/0-1 to get into the ports at the same time to enter the IP DHCP Snooping trust command. So these are all the interfaces on the switch. So we want 0, 2, 0, 3, 1, 0, and 1, 1 to not be trusted. By default, they are not trusted, but we still need to set the DHCP limit rate on the interfaces. So we use the command interface range gigabit Ethernet 0/2-3, comma, gigabit Ethernet 1/0-1 to get into all the untrusted interfaces at the same time. Then we're going to enter the IP DHCP Snooping limit rate 8 command. We'll use the show IP DHCP Snooping command to verify gigabit Ethernet 0/0 and 0/1 are trusted, their rate limits are unlimited. And now that we've set the rate limit to 8 on the untrusted ports, they will appear in the show output. If you leave the default commands, the untrusted ports do not appear in the show output. But by modifying the rate limit, that allows the show output to include the untrusted ports. So that concludes the DHCP Snooping configuration. Next, we're going to move into the Ipr Inspection Configuration. The first thing we'll do is enable the feature on the VLAN that we want it to be enabled on. In this particular example, we're only working with VLAN 1, so the command will be Ipr Inspection VLAN 1. Next, we'll enter the error disable recovery cause ARP inspection command. We've already set the interval, we've just added a second cause, which is the ARP-inspection. Next, we'll go into the interface configuration mode for our untrusted ports. We've already entered them one time during the DHCP Snooping configuration, so we can just use the up arrow to get back to the interface range gigabit Ethernet 0/2-3, comma, gigabit Ethernet 1/0-1 command. So now that we're back in the untrusted ports, we can use the IP ARP inspection limit rate 8 command. And this particular command, you can also have a burst interval setting, and we'll set that to 4. Now we use the show IP ARP inspection command to verify that the feature is enabled. Next, we use the show Ipr inspection interface command to show us the trusted or untrusted state of the port. It also shows us our rate in packets per second, which we set to 8, and our burst interval, which is set to 4. Now we'll use the interface range gigabit Ethernet 0/0-1 command. We want these ports to be trusted because they're the ports that are connecting to the routers. Once we're in interface configuration mode, we enter the Ipr inspection trust command. We'll use show Ipr inspection interfaces again, and now we can see that the interfaces are trusted. So one more feature we'll talk about for the Ipr inspection configuration is the validate command. The three options for the validate command are source MAC, destination MAC, and IP. First, we'll demonstrate how to turn on the Ipr inspection validate for the source MAC. We enter the command and use the do show Ipr inspection command. And here at the top, we can see that we've enabled source MAC validation. Now we'll enable destination MAC address validation. And when we do this, it disables the source MAC validation. So we'll use the show Ipr inspection command to verify at the top of the show output here that we've enabled the validation by destination MAC address. Now what we'll do is we'll enable all three at the same time by entering the Ipr inspection validate, source MAC, destination MAC, and IP. When we do this and look at the show put, we can now see that the three validations are enabled. So we're going to return the validation to the default setting, which is all of three features are disabled. So all we have to do is use the up arrow and then put the no command in front of the previous command. And now when we do the show command, we can see that the validations are now disabled. Now that we've completed the Dhcp snooping and dynamic ARP inspection configuration on the Snoop Switch, we will now go into the branch 1 router, go into interface gigabit Ethernet 0/1 to give it the IP address 172.16.1.1, 255.255.255.0, followed by the no shutdown command to enable the interface. We're also going to have the interface participate in the Ospf routing protocol. So in interface gigabit Ethernet 0/1's configuration mode, we'll enter the IP Ospf 50 area 0 command. And so now the Snoop Switch network will participate in the Ospf routing protocol. Now we will focus on branch 1 and configuring it to be a Dhcp server. We're going to use a /24 network, so we'll have 254 usable IP addresses. So the first part of the configuration, we enter the IP Dhcp excluded addresses command to exclude the first 5 IP addresses in the range for our default gateway on branch 1 and the IP address for the interface on expansion 1. So now we have to define the Dhcp pool. We do this with the IP Dhcp Pool command. We'll call this pool 1. Once we enter this command, we're in Dhcp configuration mode. We have to have a domain name when we do Dhcp configurations. So we enter the domain-name command, and then I used example.com for this particular example. Next, we need to define the Dhcp pool. The subnet is this 172.16.1.0, and it will be a /24 network, so the dotted decimal notation for the subnet is 255.255.255.0. Now we enter the default router 172.16.1.1 command to define the default gateway for the Snoop Switch network. There's also a DNS-server command to set your DNS server IP address. And then this final lease command, which is in days. So this is a lease for 7 days. So we'll power on the desktops, and then they'll go through the DHCP DORA process, which is where the desktops will send out a discover message. The server responds with an offer message. The desktop responds back with a request. And then the DHCP server finishes with an acknowledge, and then that acknowledgement message will have the IP address for the desktop. So now that we have the PC powered on, we enter the IP adder command, and we can see that it pulled the 172.16.1.6 IP address. We excluded the first 5 IP addresses, so the first available address in the range was a 6, and that's why it chose the 6. We'll power on the other 2 desktops, and they'll start pulling their IP addresses from the server as well. Now what we'll do is we're going to define the expansion network's DHCP range. So before we do that, we exclude the addresses in the range with the IPDHCP excluded -addresses command. And then we're going to exclude only the one IP address for the default gateway. So now we'll define the DHCP Pool 2 with the IPDHCP Pool 2 command. We'll use the domain-name command and use example.com for the domain name. Next, we'll define the network as 192.168.254.0, 255.255.255.0. Then we'll define the default router, which will be 192.168.254.1, followed by the DNS-server command. In this case, we'll use 8.8.8.8. And then finally, the lease command, which again is in days. So this IP address will be leased for 7 days. While the expansion 1 router finishes booting up, we'll go over to the Snoop Switch. We're going to check out the Dhcp Snooping binding table by using the show IP Dhcp Snooping binding command. In the show output, we can see the 4 IP addresses that were assigned to our desktops by DHCP, their MAC addresses, and their port interfaces. So the Dhcp snooping process builds this table, and then the dynamic Ipr inspection configuration uses that information to either filter or allow Ipr traffic. So now expansion 1 is booted up. We'll do our initial configurations. We'll give it the host name of expansion 1, and then get our logging asynchronous command in the line configuration mode to continue keeping our syslog messages looking clean during the configurations. So first we'll go into Gigabit Ethernet 0/1, configure the IP address 172.16.1.2, 255.255.255.0 command. We enable the interface with the no shutdown command. So this will give us connectivity between expansion 1 and branch 1. Now we'll go into interface configuration mode for Gigabit Ethernet 0/1 to configure the IP address that will act as the default gateway IP for this second expansion 1 network. So we enter the command IP address 192.168.254.1, 255.255.255.0. Then we enter the IP helper address 172.16.1.1 command, followed by the no shutdown command to enable the interface. For the initial configuration, we'll have a static route from branch 1 to the second DHCP network. We'll use the IP route 192.168.254.0, 255.255.255.0, 172.16.1.2 command to configure the static route. The 172.16.1.2 will be the expansion 1 Ethernet interface facing branch 1. The expansion 1 router will be using the IP-helper address command. So when it communicates with branch 1, it needs a static route back to the 192.168.254.0 network. When we move back into branch 1 and enter the show IP DHCP binding command, we see in the show output we've got our assigned leased IP addresses and the MAC address of the desktop that they were assigned to, and the date that they were assigned. We can also use the show IP DHCP pool command. The show output lets us know that 0 IP addresses have been leased on the expansion 1 network, the range and the current index. When we look at DHCP pool 1, there's been 6 IP addresses assigned and the current index is .12. So now what we'll do is we'll power on our desktops. They'll communicate with the expansion 1 router, use the IP helper address command to forward the DHCP messages to branch 1. The port on the Snoop Switch facing expansion 1 is trusted, so the DHCP messages can flow from the expansion 1 router to the branch 1 router. Now that the desktops are powered on, we'll go into this desktop, look at its IP address, and we see that it's got the 192.168.254.4 IP address. And then we'll go back into the branch 1 router, enter the show IP DHCP binding command, and then we can see the 4 desktops have pulled their IP addresses, the 2, 3, 4, and 5. When we come back down to the show output and look at the current index, it's 192.168.254.6. So if we plugged in another PC, that would be the next IP address that would be assigned. This will finish our DHCP configurations for this upper left-hand corner topology. So what we are going to do next is advertise the 192.168.254.0 network on our Ospf area 0 network. So first we're going to enter the interface configuration mode for Gigabit Ethernet 0/1, enter the IP Ospf 50 area 0 command. Then we're also going to enter the interface configuration mode for Gigabit Ethernet 0/0 to enter the IP Ospf 50 area 0 command. Now the neighbor adjacency forms with the 1.1.1.1 router, which is the branch 1 router. Next, we're going to change the router ID on expansion 1. So we'll enter router configuration mode with the router Ospf 50 command, and then use the router-ID 0.0.0.1 command. So we'll come back to the secure zone router, use the show IP route Ospf command, and now we can see our new 192.168.254.0/24 network is part of the routing table. And so now we can do some test pings. I'll ping one of the desktops on the 192.168.254 network, the .3 desktop, and we can see we got a response. Now we are going to move to this upper right-hand corner topology, turn on this security switch, and then we're going to copy the IP configuration from this VLAN 80 PC and then paste it into our secure zone PCs. We're going to have them be static IP addresses all in the same subnet. The subnet's going to be 10.77.77.0/29, which gives us 6 usable IP addresses in the subnet. The first IP address here will be 10.77.77.6 with its default gateway of 10.77.77.1. So now we can copy and paste this configuration into the next desktop, and then all we have to do is modify the IP address. So this telnet PC will be 10.77.77.5, and the IP PC will be 10.77.77.4. We'll go into the secure zone router into interface gigabit Ethernet 0/1 to enter the default gateway IP address, which is going to be 10.77.77.1 and then 255.255.255.248. That is a /29 subnet, and that gives us 6 usable IP addresses. Now we enter the no shutdown command to enable the interface, followed by the IP Ospf 50 area 0 command to have the subnet participate in the Ospf routing protocol. So while these desktops are booting up, we're going to finish building the topology for the video. So we're going to move to the top of the topology, and we're going to drag out 2 switches that'll connect to core 1 and core 2. Then we're also going to drag out 2 routers. One will be hot swap router 1, the other will be hot swap router 2, to demonstrate some hot swap routing protocol concepts. And then another switch that will represent the internet service provider, which is our gateway to the internet. We label the top switch ISP, this first router Hsrp1, and the second router Hsrp2. Next, we're going to label this lower left-hand switch H-switch1, and then the switch on the right H-switch2. So we'll kind of straighten everything up here, and we'll make our connection from H switch 1 to core switch 1, and then H switch 2 to core switch 2. So we'll start making our last few connections of the video. So we'll connect Hsrp 1 to H switch 1, Hsrp 2 to H switch 2, and then we'll connect Hsrp 1 to Hsrp 2, connect Hsrp 1 to the ISP, and then connect Hsrp 2 to the ISP. And the last connection we need to make is between H switch 1 and H switch 2. And then we're going to plug in these two desktops off of the switch to act as our Hsrp admin desktops. We'll go in and label this left side PC Hsrp admin 1, and then the right side desktop Hsrp admin 2. So we'll return to this right side secure zone topology. So now that everything's booted up, we're going to do some test pings. We're going to ping the 192.168.254.0 network. We'll ping the .3 PC, and we can see we got a response. So we have network connectivity all the way into our second Dhcp network. Then we also have connectivity to the 192.168.8.0 network, which is in the lower left hand of the topology. So the secure zone PCs are able to touch every part of the network, except for the Area 51 part of the network. Now that we've established the connectivity throughout the network, we can start using access lists on the secure zone router to determine what traffic we want to flow into the network. Standard access control lists can only filter traffic by source IP address. So best practice dictates to put the standard access control list as close to the destination address as possible. In this particular case, it's going to be the secure zone router. So we use the command access list 8 deny host 192.168.8.100 to deny that host's traffic from entering this network. Standard access lists have an implicit deny statement at the end of them. What that means is it will deny all traffic by default. So we have to put in this access list 8 permit any statement to allow the other types of traffic on the network access to this network. Part of the ACL configuration process is setting the direction that the access list control list functions in. So what we'll do is enter gigabit Ethernet 0/0 to enter the IP access group command. We have to put in the name of the access list, which is 8, followed by direction. In this case, it's in because our gigabit Ethernet 0/0 port is on the left side of the router. To verify the ACL is working, we can do a test ping from the 192.168.8.100 PC. We'll try to ping one of the PCs on the secure zone, and the ping fails. So now we'll come over to a different PC, the 192.168.7.100, and then when we try to ping a PC in the secure zone, we're able to ping the desktops. So we'll generate an SSH login attempt from 192.168.8.100. The connection will be refused. So that's also an indication that our access list is working. Then we can also go to the router and use a show IP access lists command. And the show up lets us know how many matches have happened per condition since the access list has been implemented. Next, we're going to move into extended access lists. Best practice dictates for the extended access list that they be placed closest to the originating address as possible. So we're going to make an access list that's going to affect the Dhcp networks. So first we use the command IP access-list command followed by the keyword extended. Then we put the name of our access list. In this case, it's block subnet list. Once we enter that command, we go into ACL configuration mode. Now we can enter the deny and permit statements. This first example will be denying all IP traffic from the 172.16.1.0 subnet to the 10.77.77.0 subnet. And we use the wildcard masks. So the /24 is the 0.0.0.255, and a /28 is the 0.0.0.15. The subnet is a /29, so this will block additional IP addresses if there's ever expansion in the future. Just like with standard access lists, extended access lists have an implicit deny statement at the end of the access list by default. We have to use a permit IP any statement to allow the other types of traffic out into the rest of the network. So we enter the permit IP any command to allow the other types of traffic. We have to configure the direction of the access list. So we enter the interface configuration mode for Gigabit Ethernet 0/0 to enter the IP access -group command. We put in the name of our access list and then the direction that we want the access list to operate in. In this case, it will be out. Now we can do some testing to verify the ACL is working. So first we'll go into a PC on the Dhcp Snooping network. And then we'll try to do a ping to the 10.77.77.0 network. So we go in and we ping 10.77.77.4, and we can see that we're not getting the response. And now we'll come over to the second Dhcp network, which is a 192.168.254.0 network. And then when we ping the secure zone network, it succeeds because the access list is not denying traffic from that subnet, only the 172.16.0 network. We can also verify on the router by using the show IP access list command. We can see our block subnet list, access list with the permit and deny statements. And then we can see the matches from the 172.16.1.0 network that were denied, and then the matches for the other types of traffic that were allowed. We move back into the central router to configure a extended access list. This one is going to block the telnet traffic from PCs VLAN 10 through 80. to going to the secure zone. The other types of traffic the PCs generate will be allowed through. So we enter the access control list configuration mode by entering the IP access-list extended block telnet list command. This also names the extended access list. We start the command with deny TCP 192.168.0.0.0.255.255. What this does is any IP address that begins with 192.168 will be filtered. So all of these addresses, all of these subnets, even though they're different, the first two octets are the same. So by using the wildcard mask in this way, any IP addresses that match these 192.168 in their first two octets will be a match for the access control list. The next part of the command defines the destination subnet. In this case, it's the 10.77.77.0.0.0.15 network. This blocks additional IP addresses to the /29 network. That way, if there's ever expansion, we won't have to alter the access list. Then we use the EQ parameter, which represents equals, and then we enter the number 23, which represents the well-known port of 23, which is the port used when creating a socket for a telnet connection. And like with the other access control lists, we enter the permit IP any statement to allow the other types of traffic into the network. Before we apply the direction to the interface for the ACL, we're going to do some testing. For the Cisco modeling labs, when you want to telnet into the desktops, you have to go into super user mode. So you enter the sudo su command, followed by the password, which is Cisco, and then you have to enter the telnet d command. Entering this command will allow us to telnet into this PC in the secure zone. We haven't applied our ACL in a direction yet, so the ACL is not turned on. So we'll test the telnet connection to make sure that it works. And here we can see that we were able to telnet into the 10.77.77.5 PC. So we'll exit from the telnet connection, and then we'll go back into the central router into interface gigabit Ethernet 0/0. And then we'll enter the command IP access -group, and then the name of our access list, which is block telnet list, followed by the keyword out to set the direction of the access list. So now we'll go back into the PCs and we'll try a secure shell connection. The secure shell connection will succeed because the access list is only blocking on port 23. Secure shell tries to make connections on port 22, so it will be allowed through. So when we try the SSH connection, we're able to get into the PC. And here we got into the 10.77.77.5 PC. But now on the PC that we were able to telnet earlier, we try to telnet, the connection is refused. We tried a second time, the connection is refused. So to verify everything, we go into the central router, do the show IP access list command, and we can see here we have the two matches for our two denied telnet attempts, and then all the other matches for the traffic that was allowed through. The last access list we'll configure is going to be on the expansion 1 router. It'll be identical to the telnet access control list, except for this one will be blocking the secure shell port of 22. So we start the configuration with the IP access -list extended block SSH list command. This allows us to enter ACL configuration mode, and it names the access control list. So we begin with the deny TCP 192.168.254.0.0.0.255 part of the command. This defines the source subnet, which is our 192.168.254.0 network. Next, we'll enter the destination subnet, which is 10.77.77.0.0.0.15. The wildcard mask for the secure zone would be 0.0.0.7, but we're planning for expansion in the future, so we use the next subnet mask up. This way we won't have to alter the access list if there is expansion. Then we use the EQ parameter, which represents equals, and then we enter the number 22, which is for the secure shell port. We also enter the permit IP any statement to allow the other types of traffic into the network. So again, before we apply the access list to the interface and its direction, we're going to do some testing. So the first test we're going to do is a secure shell connection to the PC 10.77.77.5. We can see the connection works, and we are on the secure zone network. So now we'll exit from the connection. We'll go back into the expansion 1 router, and we'll apply the ACL to the gigabit Ethernet interface 0/0. So in interface configuration mode, we enter the IP access -group block SSH list out command. I misspelled block list there, so I re-enter the command IP access -group block list out. And this will apply the ACL and its direction to the interface. So now when we go back into the PC that we were able to secure shell with earlier, we attempt to do the secure shell and the connection is refused. We try it again, the connection is refused. However, the other types of traffic are still allowed. So when we try to ping to the same IP address, the ping traffic is allowed through the access list. So now we go back into the expansion 1 router, do a show IP access list, and the show output will show us that we had 2 matches for blocked SSH attempts, and then the ping traffic, the 4 pings were allowed through. That's the last access control list we'll be configuring. Now we're going to move to the top part of the topology to configure these top 2 routers and the switches for the hot swap routing protocol. We're going to go into the Hsrp admin PCs and assign them static IP addresses. This first one will be 10.10.10.6. And we also need to change the subnet mask to a /26. We also need to set the default gateway. We're going to use the IP address 10.10.10.30. The /26 subnet gives us 30 usable IP addresses. So the .30 address is the last usable IP address in the range. So we're going to use that as our hot swap routing protocol's virtual interface. That will be our default gateway. So for now, we'll just statically assign that IP address to these PCs. And then we're going to go into the routers and configure the hot swap routing protocol. So now we come to Hsrp admin 2, just modify, copy and paste the configuration and just modify the IP address from a 6 to a 7. Save the configuration, and now the PCs are ready to go. So now we're going to boot up all our devices, let them get loaded up, and then we're going to start the Hsrp configuration. So we'll start with hswitch1. We'll give it its host name by using the hostname command in global configuration mode, followed by hswitch1. Then we'll enter line configuration mode and enter the logging synchronous command to keep our syslog messages looking clean. Then we're going to enter interface gigabit Ethernet 0/2's interface configuration mode to enter the switch port encapsulation .1q command, followed by the switch port mode trunk command to have the link between hswitch 1 and 2 act as a trunk link. So now we'll come over to hswitch2, configure the host name, followed by the logging asynchronous command in line configuration mode. And now we'll go into interface gigabit Ethernet 0/2, which is the port connecting to hswitch1. And we're going to enter the switch port trunk encapsulation .1q command, followed by the switch port mode trunk command to have this link act as a trunk link. So now we'll move into global configuration on the hot swap router 1, give it the host name Hsrp1. We'll enter router configuration mode with the router Ospf 50 command. We'll have this router participate in our Ospf configuration. We'll give it a router ID of 9.9.9.9. Now we'll go into the interfaces and assign them the IP addresses, and then also advertise their networks to the Ospf network. So the first interface we'll go into is gigabit Ethernet 0/0 to enter the IP address 10.10.10.5, 255.255.255.224 command. We also have to enter the no shutdown command to enable the interface. And so now we have an active interface in our 10.10.10.0 network. We'll use the IP Ospf 50 area 0 command on the interface so that this router will begin to participate in the configuration by advertising the network on the interface. And here we can see our adjacencies have formed, and now when we do the show IP route Ospf, we have our shared Ospf configurations. I had to turn a lot of them off for performance during this part of the video, but these are the current Ospf routes in our network. These bottom 8 subnets, as you can see, the switches are turned off. It also highlights an important concept for dynamic routing protocols. When I turn the VLAN 10 through 80 subnets router off, the dynamic routing protocol messages updated all of the Ospf routers with the current active routes. So when VLANs, subnets 10 through 80 were shut down, the dynamic routing protocol updated all of the routers. We'll go back into Gigabit Ethernet 0/0's interface configuration mode to configure the Hotspot routing protocol. We entered the standby 30 IP 10.10.10.30 command. This is what sets the virtual interface's IP address that'll act as the default gateway for our Hsrp admin 1 and 2 desktops. We also have to set the standby version. We're going to set it to version 2. Then we're also going to give it the standby group name of Hsrp with the standby 30 name command. And then we'll set the priority with the standby 30 priority 110 command. In the Hotspot routing protocol, the higher the priority is what determines if the router is active or not. So the router with highest priority will be the active router, and the other router will be in standby mode. Now we get our syslog message letting us know that this is the current active router, changed its state from standby to active. We'll set Hsrp2 with a lower priority, which makes Hsrp1 the active router. Next, we need to go into the port facing Hsrp2, so we use the interface Gigabit Ethernet 0/1 command to enter interface configuration mode. And then we use the IP address command to configure the IP address 10.44.44.1, 255.255.255.252. We enter the no shutdown command to enable the interface. That completes the Hsrp configuration on Hsrp1. Now we'll move into Hsrp2 to configure its hot swap routing protocol. So first we'll go into the router and give it its host name of Hsrp2 and enter the logging as synchronous man in line configuration mode. Then we'll enter the router Ospf 50 command to enter router configuration mode. Now we set the router ID to 10.10.10.10. We'll go into interface Gigabit Ethernet 0/1's interface configuration mode, which is the port facing Hsrp1, to enter the IP address 10.44.44.2, 255.255.255.252 command. Then we use the no shutdown command to enable the interface. So now I use the do ping 10.44.44.1 command to verify that we have IP connectivity. There we can see we've got our response. The hot swap routing protocol requires us to have this IP network in between the routers. We'll enter interface Gigabit Ethernet 0/0's interface configuration mode to enter our Hsrp commands. First, we'll set the IP address to 10.10.10.6, 255.255.255.224. We'll enter the no shutdown command to enable the interface. and then enter the IP Ospf 50 area 0 command to have it participate in our dynamic routing protocol. Now we enter the standby 30 IP 10.10.10.30 command. This will set our virtual IP address that's shared between Hsrp 1 and 2. With the hot swap routing protocol, that virtual interface is what's used as our default gateway, which is why we statically assigned Hsrp admin 1 and 2 that IP address for their default gateway. Next, we'll enter the standby version 2 command to set the version. And then we'll enter the standby name Hsrp command to name the Hsrp group Hsrp. And then we'll set the priority to 90 with the standby 30 priority 90 command. This will configure Hsrp2 to be in standby mode because it has a lower priority setting than Hsrp1. So that will finish the hot swap routing protocol between Hsrp1 and Hsrp2. Now we can power on the Hsrp admin 1 and 2 PCs, and while they're booting up, we'll move into the central router and we'll ping the virtual IP address of the Hsrp network, and then we get a response, so that helps us to verify that the configuration is correct. We'll continue the testing by moving into the secure zone router and pinging the virtual IP address. And then we can see that we've gotten a response. We're also going to move back into the 192.168.254.0 desktops and try to ping the virtual IP address. Then we can see we've gotten a response. Now that Hsrp admin 1 and 2 are booted up, we'll go into Hsrp admin 2 to test ping the virtual IP address, and we get a response. Then we'll also go into Hsrp admin 1, do a ping test, and we can see that we're getting a response. We use the interface range gigabit Ethernet 0/0-1 command to enter the interface configuration mode for the 2 ports, and then we'll shut them down. So what will happen is Hsrp2 will move from standby mode to active mode, and the same virtual IP address is still active because we've configured it on both of the routers. So when Hsrp1 goes down, we still have IP connectivity to the virtual IP address through Hsrp2. So now we do a test ping after we shut down the interface from the 192.168.254.0 network. Then we can see we're getting a response. And then I come back to Hsrp1, do a do show IP interface brief to show that the status is administratively down, which means that Hsrp2 is now acting as the default gateway, the active router in the Hsrp process. Back in Hsrp2, we can see we got the syslog message there that the state went from standby to active. So that also verifies that our Hsrp configuration was correct. So now we're going to use the interface range gigabit Ethernet 0/0-1 to enter the ports on Hsrp2 and then shut them down. So now when we go back to the 192.168.254.0 network, do a test ping, it fails because none of the interfaces are up. We move back into the Hsrp1 router and we're still in interface configuration mode for the ports that we shut down. So now we'll just enter the no shutdown command to re-enable the ports. So we'll get syslog messages that our interface is back online, but they still need to form their router adjacencies before IP connectivity can happen. So now when we go into Hsrp1, we can see our neighbor adjacencies have just formed. So now the hotspot routing protocol can be re-enabled. And so now when we do our test ping from Hsrp admin 1, we get a response. We left this PC on the 192.168.254 network in a perpetual pinging state. So we didn't have to enter the command. It just started getting the ping responses and started displaying the output. And now when we end the ping command and look at the statistics, we can see of the 67 packets that were transmitted, only 11 of them were received because the interface wasn't active. We made the interface active. It started gathering the ping statistics. And then when we ended the command, it presented us the statistics for the ping session. We're still in the interface configuration mode for the ports on Hsrp2. So we're going to re-enable them with the no shutdown command. We'll wait for the syslog messages to let us know the interfaces are up and the adjacencies are back. And that will conclude the Hsrp testing that we'll be doing. In the video so far, we've configured these devices that are highlighted in blue. This represents the network that we have control over and could implement our administration policies like a IP addressing scheme, for example. This top switch represents the ISP switch, which we have no control over, and it's going to represent our default gateway to the internet. Basically, we'll have an IP address that none of the routers know, and then we'll have IP connectivity to it by relaying the default route information to all the other routers. So we will go in and do the initial configuration by giving it its host name of ISP and then entering the line console configuration mode to enter the logging synchronous command. So we're going to configure a loopback interface on this ISP switch to represent our IP address for the host that is out in the internet. So we give it this 209.165.16.17 255.255.255.0 IP address. And then we enter the no shutdown command to enable the loopback interface. And so now our goal is going to become to communicate with this loopback interface that is representing our host IP address somewhere out on the internet. We have to configure two different subnets, one connecting to Hsrp1, one connecting to Hsrp2. The port facing Hsrp1 is gigabit Ethernet 0/0. So we'll start by going into interface gigabit Ethernet 0/0's interface configuration mode. And we enter the no switch port command to turn the port into a routed port. We'll then assign the IP address 10.55.55.2 255.255.255.252. Now we'll move into Hsrp1 to configure the port on the other side of the link, which is Hsrp's Gigabit Ethernet port 0/2. So we go into interface configuration mode, enter the IP address 10.55.55.1, 255.255.255.252 command. And then once we can see that we've set the IP address, we'll do a test ping. So I'll use the do ping 10.55.55.2 command. And then we can see that we get a response. We'll move back to Hsrp2, and we're going to enter the interface configuration mode for the port facing the ISP. So it's going to be interface Gigabit Ethernet 0/2. In the interface configuration mode, we enter the IP address 10.66.66.1, 255.255.255.252 command, followed by the no shutdown command to enable the interface. Now we'll go into the ISP switch to the port facing Hsrp2, which is Gigabit Ethernet 0/1, and we'll enter the IP address 10.66.66.2, 255.255.255.252 command, followed by the no shutdown command. So now we'll do a do ping 10.66.66.1 command to verify IP connectivity. And then here we can see we've got a response. During the video, I had to power down devices during the initial configuration to give me better performance. So now we're going to come back and turn a lot of these devices back on. When you look at my GitHub website for this video, it'll have the scripts for each device that you can download. So here I've got a script for dist1, the configuration for dist1. It's a simple text file. We open up the text file, and then we just copy and paste the dist1 configuration from the text file directly into the console of the Cisco Modeling Lab. So we have to start in global configuration mode for these particular text files. So I copy it from the text file, right-click on the console, and then paste. And now we can see the commands are being entered one at a time. And then as the device comes online, we'll get syslog messages about interfaces coming up, VLAN states changing their state to up, and neighbor adjacencies with the Ospf. I could have used a write memory or a copy running config startup config and then shut it down. But I wanted to demonstrate the copy and paste functionality that the Cisco modeling platform offers. When we start doing our test pings on the loopback interface, there needs to be a route from the loopback interface back into our network. So we're going to use the IP route 0.0.0.0, 0.0.0.0.10 10.55.55.1 command. The 10.55.55.1 is our next hop IP, and then this is a default route. What that means is if the router doesn't have a route to the destination IP address, it will forward the traffic, in this case, the next hop IP address, which is 10.55.55.1. We'll also set another static route to Hsrp2 using the next hop IP address of 10.66.66.1. And this is so that we can do our testing for exiting our network with a default route. We will be configuring default static routes on Hsrp1 and Hsrp2. We'll start with Hsrp1. In global configuration mode, we enter the IP route 0.0.0.0, 0.0.0.0, 10.55.55.2 command. The 10.55.55.2 is our next hop IP address on the ISP. So now we need to go into Hsrp2, configure a default static route on it. So we'll go into global configuration mode to enter the IP route 0.0.0.0, 10.66.66.2 command to configure the static route as having the next hop IP address of the ISP. With the Ospf routing protocol, you can designate a router to advertise the default route to all the other Ospf routers. The command also has a metric parameter, and the default information originate command with the lowest metric value will become the default route that is advertised. So when we enter the default information originate command, we'll come over here to the branch 1 router. When we do a show IP route, we can see at the top of the routing table, the gateway of last resort is set to 10.10.10.6, which is the IP address of the interface facing the 10.10.10.0 network off of Hsrp2. The expansion router is one hop away from the 10.10.10.0 network. When we do the show IP route command to look at the routing table, we can see that the gateway of last resort is set to the interface of branch 1 facing the Snoop Switch network. So what happened was the default route got pushed to branch 1. Branch 1 pushed the default route to expansion 1, letting it know what the next hop IP address is, which is 172.16.1.1. And then when it gets to the branch 1 router, the gateway of last resort becomes 10.10.10.6 to reach the default route, which then pushes it out to the internet to reach the 209.165.16.17 address. So now we'll ping the loopback interface on ISP1 from the 192.168.254.0 network, and we can see that we're getting a response. So even though we don't have a route to the 209.165 network, when the router can't find a route, it has a route for the default route, which sends all traffic that doesn't have a routable IP address to that default route to then be routed to its destination, if it exists. Now we've come back to Hsrp1 to enter the default information originate command on it. The default metric is lower than 5. So what will happen when we enter this command with no metric parameter is it will have a lower metric than the one on Hsrp2. With that lower metric, Hsrp1 will now dictate the default information command. It will now relay itself as the default route. So we'll come over to the central router and we'll do a show IP route command. And then again at the top of the show IP route output, we can see the gateway of last resort has been set to 10.10.10.5, which is the Hsrp1 interface facing the 10.10.10.0 network. So to get to the default network, you have to go to that 10.10.10.5 IP address. So since it had the lower metric, it now will replace this 10.10.10.6 route on all of the routers to the gateway of last resort being this 10.10.10.5. So the reason we did that is that if one of the routers were to go offline for some reason, then the other default information originate with the metric 5 would take over and the network wouldn't go down. We would just lose the one device and the network could keep operating. So now we can run a demonstration scenario where Hsrp1 goes offline. So all of the network traffic now must flow through Hsrp2. So when this happens, the ISP realizes Hsrp1 is offline. So one of the internet service provider admins goes into the port facing Hsrp1 and shuts the port down with the shutdown command. When this happens, there's a backup default static route with an administrative distance of 5. So when this interface is shut down, the IP routing table updates the gateway of last resort from 1055.55.1 to 10.66.66.1. And so now we lost Hsrp1, but we still have our IP connectivity outside of our network, which is represented by IP connectivity to the loopback interface on the ISP. And we can see we're getting responses from our ping command, which means we still have IP connectivity outside of our network. There are features in the Cisco IOS platform that need a username password set. So we're going to go ahead and create one by using the username secret command. So first we enter the username mark to set the username to mark, followed by the parameter secret and the characters of the password. So there's my password in this case. The secret parameter takes your password and runs it through a hashing algorithm to produce a specific output. And then it saves that hash output in the startup configuration. So that way when you go to log in, you type in your password and it's put through the hashing algorithm, and if it matches the specific output of the passwords when it's run through the hashing algorithm, it's a match, and then you're allowed to log in. Another useful aspect of the parameter is that the hashed characters are saved in the startup configuration file, not the password. So when people are looking at the configuration file, they can only view the hashed characters and not your password. The last topic of the video is going to cover the spanning tree protocol. It's a layer 2 protocol, so we're going to be focused on this full mesh topology in the center of our main topology. The full mesh topology creates redundant links. This can create a situation where frames at the layer 2 level can loop indefinitely in the topology. The three main problems are broadcast storms, MAC table instability, and multiple frame transmission. Spanning tree protocol addresses these problems by assigning ports certain states depending on which switch is the primary root bridge. After the root bridge is defined, then the path that the frames take can be configured to not loop indefinitely in the network, creating the broadcast storms, MAC address table instability, and multiple frame transmission. So the root bridge is elected by winning the election process. The election is won by the bridge that is advertising the lowest bridge ID, which is the MAC address of the switch plus the VLAN that it operates in. And then the switch with the lowest bridge ID will become the root bridge. The root bridge will have all of its ports in a forwarding state. And then as we can see here on a switch that's not the root bridge, one of its ports will be the pathway to the root bridge. In this case, it's Gigabit Ethernet 0/3. And then when we open the connectivity tab, we can see that Gigabit Ethernet 0/3 is connected to Core 4. So now we'll go into the Core 4 switch and enter a show spanning tree command. And the show output lets us know that all of the ports are in a forwarding state, which is an indication that it's the root bridge. And then it also has this message, this bridge is the root. And that lets you know that this is the root bridge for VLAN 1. So the different spanning tree modes are rapid, per VLAN, spanning tree, regular spanning tree, and then just regular per VLAN spanning tree. And then there's also multiple spanning tree. So in global configuration mode, you would enter spanning -tree mode rapid -PVST, and that would enable rapid per VLAN spanning tree mode on the switch. Currently, Core 4 is the root bridge. The spanning tree commands allow you to have influence over the election process to determine which bridge is the root bridge. The root bridge ID consists of the VLAN plus the priority plus the MAC address. So if the priorities tie, the tiebreaker becomes the lowest MAC address. So what that means is we can change the priority parameter to influence the root bridge election. The default priority is 32,768. So if we use the spanning tree VLAN 1 priority command and set it to a value less than 32,768, that will allow the switch to win the election and become the root switch. We also have the option to enter the spanning tree VLAN 1 root primary command. What this does is it changes the priority on the switch to 24,576, which is a value lower than the default. So when you enter this command, it changes the priority to 24,576, allowing it to win an election where the other switches have the default setting. After we enter the command, we can see by the show output that all of the ports are in a forwarding state, which is an indication that this bridge is the root bridge. We can also see the priority that is 24,577. It's the 24,576 plus the VLAN value of 1, which gives it the 24,577 value. And then we also have this message that says the bridge is the root, which lets us know that now core 1 is now the root bridge. This will conclude the demonstration of the Cisco modeling platform that I've been doing to celebrate passing the CCNA exam. Thank you for watching.